Hi everyone, welcome to Lab 4, Oscillations. Here's the table of contents. So the purpose of this lab was to analyze the motion of a spring mass system. The goal was to determine if the computational model follows the energy principle. I used Newton's second law, the energy principle, and update formulas. The system's total energy remained constant at 0, which demonstrated the energy principle. So here's the main ideas. First, we have Newton's second law. So the system's change in momentum is proportional to the new force applied. In this case, the spring force plus the force of gravity equals the change in momentum. Then the system's change in energy is the sum of the work done by the surroundings and thermal energy exchange with the surroundings. In this experiment, the system is the mass, spring, and earth, while the surroundings are nothing. And then lastly, the other equations I used were velocity and position update, kinetic energy, gravitational potential energy, and spring potential. All right, now for the experiment. So here's the tracker model. The initial conditions that I had were the object's mass, the length of the stretch string, and then tracker outputted the initial position, and then initial velocity was 0. And then the graph at the bottom right plots the position of the mass in the x and y directions. So the mass of the system, as well as the initial position and velocity, were obtained from tracker, like I previously mentioned. And then to find the spring constant, I first found the oscillation period and used it to find k. I then used k to find the relaxed length of the spring. I also created variables to represent the kinetic, gravitational, spring, and total energies. Now for coding the calculation loop. First, I calculated the net force by adding spring force and force of gravity. Then I applied the momentum principle to update the object's position and velocity. And then using these quantities, I calculated the kinetic and potential energies of the system. I was then able to find the change of energy on the system. So this is the results of the code. This animation was generated by the code to show how the spring moved. The red ball shows the movement of the mass after each time step from tracker, and then the blue ball shows the path of the computational model. And then the pictures on the right show the computational model compared to the experimental model in the x and y direction. As you can see, there are some slight deviations, so this indicates possible errors like choosing an inaccurate center of mass in tracker or not accounting for work done by the surroundings, because in reality, the experiment is not an isolated system. And then some similarities and differences between the graphs are, the graphs are very similar at the beginning of the oscillations. They follow very similar paths, especially at the highest and lowest points. But over time, outside forces affect the mass, causing more variability. So, is the energy principle satisfied? Yes. The model shows that the energy principle is satisfied because delta E, which is in orange, is constant and at 0. So in our model, we said that there are no external forces acting on the system, so the change in energy must be 0, even though we have different types of energy in the system. And then comparing oscillation periods. So to find the oscillation periods in the x and y directions, I found the average of 3 consecutive periods. As you can see, the values are different depending on which direction you choose. This deviation would affect the spring constant and the graphs. And that's it. Thanks for watching.